Alrighty, so we have a warm-up right here. A speedboat travels downstream on a river, its velocity v miles per hour at certain times given in the table above. Using the left Riemann sum, what is the approximation of the total distance traveled by the speedboat from 0.5 to 3 seconds? I don't know, it's hours. We know that the area for velocity versus time graph is actually distance. So by doing the Riemann sum, you will actually get the distance. So they want the left Riemann sum, so we're going to do that as well. Then we're going to do a limit of this bad boy right here, which is very simple. We're just going to focus on this and this thing. And then for the last one, a differentiable function f has the property that when you plug in 2, you get 5, and then for the derivative, when you plug in 2, you get 3. What is the estimate for f 2.4 using the local linear approximation for f at x equals 2? At that point, what they're saying is, what is this when you center the approximation around this point? So we've done this before. We talked about how if for instance someone said, what's the natural log of 2? Well, I don't know what that is. I don't know what the natural log of 2 is. But I know what the natural log of e is. And e is very close to 2. So if I center my approximation around the value e, I can easily get a very close approximation of what 2 would be. Alrighty, so I digress. Let me erase that, and then I see erase it later. So let's do this problem. Actually, pause the video. You do it first, and then I do this problem. This one's kind of nice. They actually tell you that they want the left Riemann sum. They don't say lower, which makes things a lot easier. For instance, when you do the left Riemann sum, it means that you take the left point. And they didn't really tell us how many intervals they want. So I'm guessing that this is going to be 1, and then this is going to be 1, and then this is going to, oops. From 0 to 0.5, then 0.5 to 1, then 1 to 1.5, then 1.5 to 2, then 2 to 2.5, then 2.5 to 3. But the left points will be this one, this one, this one, this one, this one, this one, but not this one. So let's get this started. So this has been done. So we want 32 as the first value. Oh, this has been done using the right Riemann sum. I'm looking at this. Because the first value they put is 30, 16, 22, 20, and 24. They put these. Do we not care about, maybe the time was, let's check out the times. Oh, okay, there we go. We don't start at 0. We're starting at 0.5 to 3, which means that all of this stuff to left is a no-no. We don't care about that. So literally, we do the same thing. I'll go over it again. We're going to do 0.5 to 1, and then 1 to 1.5, 1.5 to 2, 2 to 2.5, and then 2.5 to 3. And we're going to not include 3. So we're going to be using this value, this value, this value, this value, this value. But we will not use this stuff right here. This stuff's not going to get used. So let's get started. The shortcut is to just pretty much take the width and just pull that out. Because you're going to be doing 1 minus 0.5 times whatever the left point is, 30, that's 0.5. 1.5 minus 1, that's 0.5 again. 2 minus 1.5. So every single time, all of these guys have a 0.5 attached to them. So you just pull that out, and you just focus on getting the y's in there. So the first y, we're going to do the left point. It's going to be 30 plus 16 plus 22 plus 20 plus 24. These are the left points. We're going to put them all in here. Then we add them up, multiply by 0.5, and we have our value over here. Number 2. The reason why this is easy is because you simply look at the leading coefficients, the end behavior, if you will. For one, I know that x to the x squared is going to grow much faster than negative x. So this one is going to get exponentially faster than this one. and we're going to end up getting a very large number divided by a lot larger number. So the estimation is going to be 0. So that's what that is. You look at the leading coefficients. It's also called looking at the end behavior of a function. And then as you go to negative infinity, this should go to 0 because the bottom denominator, the bottom has a much larger, not much larger, but just having a larger power exponent will already lead you to this conclusion. Had they been the same, we would have looked at the we would have looked at what the signs would have been and the leading coefficients. If this had like a square right here, then you would have said, okay, negative infinity is going to be, well, assuming the negative is not inside the square, this is going to give you negative infinity squared, which is positive infinity, but minus, so negative infinity. The bottom would have been positive, so the answer would have been -1. But given that the bottom has a greater power than the top, we can stop right here. We don't care about what this coefficient is and what this coefficient is. Alrighty, and then last one, doing the linear approximation centered around 2. The reason why we do that is because we know what 2 is. F of 2 is 5 and f prime of 2 is 3. So that's going to be your slope. These are going to be your sample points. So everything was pretty much given to you. So we're going to go with the point slope form. Plug in your slope. Your slope is, I guess, do this first. So you get your little y1. So your y1 is what you're going to get right here, the 5. So that's what 5 is going to be. And then your m is going to be your f prime of 2, which is 3. So that's why you have a 3 here. And then we have a x minus x1. The x is pretty much what you're trying to find out, the 2.4. And then the x1 is just the 2. So we have the 2 right there. All right, you solve that out. You have the estimation of 6.2. And that's the do now. Let's move on. All right, so today we're going to go over the fundamental theorem of calculus. There's the first one right here. Students will apply the fundamental theorem of calculus to evaluate different integrals. Essentially, you already know kind of how to do an integral, except this time we were going to be worried about endpoints. So we won't have a c. So essentially, the way it works is when you start an integral from one point to the other point, and this is the regular function, then you would simply, the answer would be the integral function of the upper limit, or the upper bound, minus the integral function of the lower one. So we're going to get exact values. And the reason why we get exact values is because they should both have the same c, given that the same function. So when you subtract them, one of them is going to be negative, then they're going to go to 0. So you don't have any c's. So here's an example. We have the integral of x squared. We know how to deal with that. Add a 1 to 2, and then that would give you 3. So divide by it. So 1/3 times x to the third plus c will be the integral. You're gonna, in the future, stop writing that, by the way, because you're gonna accept that that's always gonna be subtracted. Then you have the lower limit and the upper limit. Plug them both in. So you're gonna have 1/3 times 4 to the third power minus plus c, minus, and then 1/3 times 1 to the third power plus c. The c's will cancel, and then this bad boy will give you this value. This will give you this value. So the final answer is going to be 63/3, which gives you 21. And over here, the c's did cancel out, like we said. Let's try another one. So use the fundamental theorem of calculus. Oops, wrong color. Use fundamental theorem of calculus to evaluate this integral right here with the lower limit of 1 and the upper limit of 4. I want to give you guys a chance to pause the video and try it out yourself. You do know how to take the integral of this. It's going to be x to the 1/2. You do know how to handle that. And we just talked about plugging in the 4 and the 1. So give it a try first, and then I will reveal it. So pause the video, try it out. 1 Mississippi, 2 Mississippi. And bam, 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 magic. Alrighty, let's do this. The square root of x is the same thing as x to the 1/2. So when you add 1 to it, you're going to get 3/2. Don't forget to divide by it. So just the multiplicative inverse, 2/3. And then to the 4 upper limit 4 and lower limit 1. You can insist on writing the C if you want to, we really don't have to. By the way, this, if you want to see it graphically, it would be this area right here at the beginning. It's a radical function, and then we only want it from 1 to 4. So this is the only area we care about. So plug in the 4 first. So we're gonna have 2/3 for both cases. So let's just factor that bad boy out. What I mean by that is you essentially what would have been in here is 2/3 times 4 to the 2/3, and then 2/3 times 1 to the 2/3. Given that 2/3 is happening on both, we can just factor it out to make things easier. So square root of 4 is 2, 2 to the 3 is 8, so we have 8 right here. And then 1 to any power is just 1, so 1. 8 minus 1 is just 7. 2/3 times 7 is 14/3, and you can leave it like that. On my test, I might ask you for 3 decimals, in which case you would have 3, 4, and then 4.667 or something. I digress. So let's move on. Over here, we have an example of one that's a little bit more complex, and that's because we have 3 things now. But we do the integral as always. So do add 1, divide by it, add 1, divide by it, and then this one, add 1, divide by 1, just doesn't matter. And then you plug in 4, so that's what you get when you plug in 4 here, here, and here. And then you do the same thing, you plug in 1. Luckily, we can just write the coefficients, and you simplify it. So this is pretty much what we get for the first one, and then the other ones kind of just flip the sign. The negative would make that negative, the negative would make that positive, the negative would make this negative, which is why we have negative, positive, negative right there. All right, so let's continue. Simplify it out as much as you can, and then you will get your final answer. Over here, I will probably insist on having 3 decimals for sure. So if this happens to be the exact value, which I think it is, yeah, I would ask to have negative 10.500, and not for specific reasons. We just that's kind of how my class is. So don't think about it too much. If you think about too much, then you're thinking, and that's not in my regime, not in my house. You know what I'm saying? All right, that's all, and that concludes the video. I made the video unnecessarily longer than it needed to be. Alrighty, you guys have a fantastic day. See you guys tomorrow.